Well, welcome to POE. Today we're going to talk about an introduction to thermodynamics. What about our thermodynamics? If you rub your hands together for 15 seconds, your hands are going to warm up. And that's thermal energy. And thermodynamics is kind of the study of what the effects of that thermal energy are. Thermodynamics, the study of the effects of work, heat flow, and energy on a system. Thermodynamics is trying to understand the movement of thermal energy. Engineers use thermodynamics in systems ranging from nuclear power plants to electrical components. Thermal energy versus temperature. These two things are quite often misconstrued. Thermal energy is the kinetic energy in transit from one object to another due to temperature difference. Thermal energy is the heat. For example, if you come inside, you stick your hands on someone's neck. You've got cold hands, they've got a warm neck. There's going to be this thermal energy. It's the kinetic energy. It's the movement. It's the transfer of this energy from their neck to your hands. Temperature is just the average kinetic energy of the particles in an object. And what we mean by this is you've got an object that's, I don't know, we'll say 40 degrees Celsius or 80 degrees Fahrenheit. What this means to us then, and those aren't exact conversions, they're probably nowhere close. But temperature is if you take every single one of them particles and take a calculation of their kinetic energy and then take an average of them, that's going to be the temperature of that object. Every single molecule, measure its kinetic energy, add them all up, and then divide by the total number, and that's going to give you the temperature. Thermal energy, on the other hand, is the amount of kinetic energy that's in transit, that's being transferred from one object to the other. The person's neck is really warm, so you can calculate its temperature. But without someone's hand, cold hand being beside that neck, there is no thermal energy because there's no energy transferring away from that. As soon as your cold hand comes over that, you're going to feel that heat because your hand's cold. It's going from the hot to the cold, and we'll talk about that in a bit. If someone were to come over with a hand that's just as warm as the neck, there would be no thermal energy because there'd be no transfer of heat, no transfer of energy. Here's some temperature scales. You can copy these down. Matter is made up of molecules in motion, meaning every molecule is moving. It has kinetic energy. It's moving. The faster it's moving, the more kinetic energy it is, the higher the temperature, because it's going to have a higher average kinetic energy. An increase in temperature increases motion. A decrease in temperature decreases motion. This will happen all the way down to a projected absolute zero. This occurs when all kinetic energy is removed from an object. If temperature is measuring energy, then if we could get rid of all the energy, then there would be no temperature. And we call this absolute zero. And that's 0 Kelvin, or negative 273 degrees Celsius. Thermodynamic equilibrium is obtained when touching objects within a system reach the same temperature. So kind of that hand and that neck, as we said earlier, if you felt no heat coming off of the neck or from the hand, you'd have thermal equilibrium. Right? They're at the same temperature. When thermal equilibrium is reached, the system loses its ability to do work. There's no energy going to be transferred. So without that energy being transferred, there's no way work can be done because work is energy. Zeroth law of thermodynamics. If two systems are separately found to be in thermal equilibrium with a third system, the first two systems are in thermal equilibrium with each other. If two systems are separately found to be in thermal equilibrium, so what we're saying here is object 1 and object 2 are found to be in thermal equilibrium with the third system, meaning the thermometer. Then what that tells us is the first two systems are in thermal equilibrium with each other. So over here, if we found object 2 and object 3, if we measure them with this thermometer, and we find out that both object 2 has the same temperature as object 3, then without even comparing the two to each other or having them touch each other, we would say they're in thermal equilibrium, which means if we bring them close to each other, no energy is going to be transferred. Thermal energy, heat transfer. The transfer or movement of thermal energy. Most common types of transfer: convection, conduction, and radiation. 100% efficiency is unattainable. All processes are irreversible. So we're going to go here in a little bit. We're going to talk more about these three: convection, conduction, and radiation. First law of thermodynamics. The law of energy conservation applied to a thermal system. Thermal energy can change form and location, but it cannot be created or destroyed. Thermal energy can be increased within a system by adding thermal energy, which is heat, or by performing work in a system. So, what they're saying with the first law of thermodynamics, again, they're reminding us, energy cannot be created or destroyed. It can change form and location. So heat can change from one spot to another, and we can change that form. Thermal energy can be increased within a system by adding thermal energy. Thermal energy can be increased within a system by adding thermal energy. We can add work into a system by doing some type of work, and you're going to cause possibly... Apologies here, I keep having two little girls run by the door screaming and yelling. At any rate, so let's talk about these. First law of thermodynamics. Pumping the handle results in what on a bicycle pump? Well, you're applying mechanical energy into the system. So that mechanical energy then is going to be converted or change form into thermal energy because of friction. So you're adding thermal energy by pumping up and down on that handle. You're going to be adding thermal energy to the system because that mechanical motion is going to change into thermal energy. The total increase in internal energy of the system is equal to what? Well, the applied mechanical energy is just looking at it from the other direction. Where did the internal energy come from? The mechanical energy. Up here they're saying the mechanical energy is going to transfer into heat. Here they're saying where did the heat come from, or the internal energy? From the mechanical energy. Second law of thermodynamics. Thermal energy flows from hot to cold. We know this. All right? An ice cube. If you stick an ice cube in your hand, it doesn't go from cold to hot, meaning that the ice cube gets colder. If energy were to go from cold to hot, the ice cube would get colder and your hand would get hotter. But that's not the case. Where the ice cube is touching your hand, heat is actually leaving your hand and going into the ice cube. We know that because the ice cube starts to melt. And that's this example. Second law of thermodynamics deals with entropy. All right, is a measure of how evenly distributed heat is within a system. Right here, this has high order. All right, this is an order, meaning all of these logs are at the same temperature. All right, they're stacked neatly. They're all sitting outside. They're all at the same temperature. This over here would be disorder, meaning parts of this fire are much hotter than other parts of this fire that are not evenly distributed. Heat is not evenly distributed in this fire. Fire has low entropy when stacked and high entropy when burning. All right. All right, convection. Convection is the transfer of thermal energy by movement of fluid, liquid, or gas. When fluid is heated, it expands, becomes less dense, and it rises. Boiler heating systems circulate heat through a home without pumps through the use of convection. A lot of things work with convection. Gas-forced air at your house. If you have a gas-forced air furnace, hot air forced air furnace, I keep stumbling through that. That's going to work with convection. The hot air is going to rise to the top, and the cold air is going to go back to the basement through your cold air returns. Conduction. Thermal energy transfer. The transfer of thermal energy within an object or between objects from molecule to molecule. This right here is conduction because the hot soup is touching the sides of the bowl. If you were to touch the hot bowl later on, the bowl, it would feel hot. The spoon, likewise, if you leave it in the soup, it's going to warm up. Even if you had it in the freezer, conduction, meaning the particles are going to be touching. Conduction means touching. Right, that's it for tonight. Hope you guys enjoyed it. I'll catch you on the flip side.